There are corners of the universe so far beyond ordinary experience that the mind slides off them like water off glass. A star exists whose material is packed so tightly that a single spoonful would outweigh an entire mountain range. Somewhere in the dark, magnets spin with a force strong enough to pull apart the atoms of a human body from thousands of kilometers away. There are boundaries in space from which even light, traveling at the only speed it knows, cannot find its way back out. And there is cold so complete, so final, that it sits only 1 degree above the lowest temperature that nature allows. These are not thought experiments or the edges of speculation. They are real locations, real conditions, scattered quietly through the same universe that holds this room. None of them is close. None of them is coming. They simply exist, turning in their own silence, indifferent to the fact that anything is watching. Tonight, we visit them one careful stop at a time, without hurry, without alarm. This is not the kind of journey that asks anything of you except your attention, and even that only lightly. You do not need to take notes or hold on to every detail as it passes. The places we visit tonight are better experienced as a slow drift than a studied lecture. Think of it less as learning and more as being briefly present beside something extraordinary before moving on. If you find these quiet explorations worth your time, a like or subscribe helps other people find their way here too. That is all it takes, and it costs nothing but a moment. But once that is out of the way, none of the rest of this evening belongs to the ordinary world. Every place we visit tonight is so remote from your life that it cannot touch anything you love. The distances involved are so enormous that the word enormous barely begins to describe them. What lies out there turns in its own dark, asking nothing of us, threatening nothing we care about. So let this be an invitation rather than a lecture, a long, slow look outward rather than anything that demands effort. The extreme places we visit tonight were not chosen for their danger. They were chosen because they are the farthest edges of what the universe is built, the places where the rules bend, where matter and energy and space itself behave in ways that have no parallel in daily life. Each stop on this tour has a way of making the familiar world feel, strangely, more settled. When you understand how extreme the distant places are, the room you are in becomes a kind of sanctuary by comparison. The quiet around you is not an absence of something. It is the specific, particular calm of a place that the universe has kept gentle. That gentleness is not accidental. It is the result of being very far from everything on this list. Let your shoulders drop a little if they haven't already. Notice the weight of wherever you're resting, the press of something solid beneath you. That weight is gravity, the same force that makes a neutron star's surface smooth beyond any surface we could polish. But here it holds you at a scale so modest and so familiar that you don't have to think about it all. Gravity on Earth is so gentle compared to what waits at certain other addresses that the comparison barely translates. We will visit those addresses tonight, and when we do, the numbers will be difficult to hold. But holding them is not required. It is enough to let them wash over you, to feel their scale the way you feel the scale of the ocean without needing to count every wave. The universe is large. You are small. That combination, it turns out, is the safest one there is. This tour will move without rushing from one extreme to the next, pausing long enough at each place to let the strangeness settle. Some of what we find will be dense, almost beyond imagination. Some of it will be violent in the way that only things very far away and very long ago could be violent, which is to say quietly, without consequence, like watching a match flare through a telescope pointed at another galaxy. The further something is from you, the more its power becomes simply a fact about the universe rather than a threat. And everything on this list is far. The nearest stop on tonight's tour is still so many light years away that its light has been traveling longer than our world has existed. Distance, it turns out, is one of the most reliable forms of peace. It is worth pausing before we begin to notice what the universe is mostly made of. People imagine space as a crowded place, full of collisions and radiation and danger. But the truth is almost the opposite. Space is mostly empty, and that emptiness is not hostile, but simply vast. Between any two bright points of light lies a distance so wide and so quiet that no word in ordinary use quite fits it. The extreme places we visit tonight are islands in that emptiness, rare and remote, doing what they do without an audience or an effect on anything near them. What reaches us from even the most violent of these places is usually nothing more than a faint signal, a ripple in a detector, a number in a database somewhere. The universe shouts from very far away, and by the time the sound arrives here, it has become a whisper, and a whisper you have to build a very expensive machine to hear. There is something worth saying about why these places are part of a tour meant to be restful. The connection is not obvious at first. A neutron star, a magnetar, a black hole, the first instant of the universe. These are not words that usually appear in the same sentence as the word peaceful. But the connection is real and it holds. When something is both extraordinary and completely beyond reach, it shifts from being a source of anxiety to being something more like a wonder. A waterfall 3 miles away cannot get you wet. It can only be beautiful. The places on tonight's tour are the universe's version of that waterfall, visible across an inconceivable distance, audible only as the faintest record of their passing, entirely unable to reach you where you are. Their extremity becomes, with distance, a kind of gift. So settle into wherever you have put yourself for this. Let the ceiling or the darkness above you stand in for the sky. Let the temperature of the air around you remind you of how narrow the band of comfortable conditions is, and how remarkable it is that you are inside it. There's a single degree above absolute zero, a cold so thorough it is almost indistinguishable from no temperature at all, and it exists in a cloud somewhere in the galaxy. You are warmer than that by several hundred degrees. The neutron star we will visit first has a surface gravity 100 billion times stronger than what keeps your feet on the floor right now. You are held here with exactly the right amount of force. None of this is coincidence exactly, but none of it feels fragile tonight either. Before the tour begins in full, it is worth naming the quality of attention this journey asks for. It is not the attention of a classroom or a briefing. It is something closer to the attention you give a window on a long flight, when the clouds below are interesting but not urgent, when you are present without being gripped. The places we visit tonight reward that kind of looking. They are strange enough to be worth noticing. They are far enough away that noticing is all that is asked of you. There is no quiz at the end, no detail important enough to keep you from drifting if that is where the night takes you. The tour is here when you are, and it will still be here in the morning, shaped into whatever you carried of it into sleep. Let the day go, then all of it, the weight of the morning, the unfinished things of the afternoon, whatever the evening brought in. None of it travels well to the surface of a neutron star. None of it has any standing in the silence between galaxies. You are warm. You are held. The most extreme places in existence are turning quietly in the dark, impossibly far from here, building nothing and threatening nothing, simply being what they are. We will go to them now, one stop at a time, unhurried and unafraid. Let's begin. The first stop on this tour sits at the far end of what matter is even capable of becoming. Somewhere in the dark, a star has died, and what it left behind is not wreckage, but something almost architectural in its precision. A neutron star begins where ordinary physics quietly surrenders, where the rules that govern the world, simply stop applying. It is not a place that threatens you, but it is a place that insists on being taken seriously before the night softens it into something peaceful. The collapse that made it happen in less than a second, the core of a giant star folding inward faster than thought. What remained after that fall is a sphere roughly 20 kilometers across, no wider than a mid-sized American city from one edge to the other. Inside that modest diameter sits more material than our entire sun contains, pressed into a shape so dense that the word dense itself starts to feel inadequate. Nothing about this object resembles anything you have ever touched or stood on or looked at from a window. And yet it is real, it is out there, and for the next few minutes, it is worth letting its strangeness sit with you without rushing past it. The numbers that describe a neutron star are the kind that the mind accepts as words before it accepts them as facts. A single cube of its material, the size of a sugar cube you might drop into a cup, would weigh approximately 1 billion tons on Earth. That is not a metaphorical billion or a loosely estimated one, but a number derived carefully from the density of matter packed to the point where the spaces between atoms have been crushed entirely out of existence. Picture a mountain, A real one with ridgelines and snowfields and a base that spreads across many miles of ground. Now, picture that entire mass folded into something small enough to rest in your closed hand. The material does not merely weigh a great deal in that volume. It is structured differently from anything else. Its neutrons press shoulder to shoulder with nothing separating them at all. Ordinary chemistry, the kind that holds your body together and keeps the table solid beneath a lamp, has no foothold here. The usual rules between atoms were not bent or strained in the making of a neutron star. They were simply left behind. Gravity at the surface of such a star is where the imagination tends to stall, and it is worth letting it stall briefly rather than rushing past the number. At the surface of a neutron star, gravity pulls approximately 100 billion times more powerfully than it pulls on you right now. To get some purchase on that ratio, consider a small and simple thing. An object released from a height of just 1 meter, a distance you could step across, would strike the surface traveling at thousands of kilometers per second. Not slowly, not with the modest thud of something dropped on a kitchen floor. At thousands of kilometers per second, which is a fraction of the speed at which light crosses a room. The star uses that gravity to pull itself into a shape so smooth and so perfectly spherical that no human instrument has ever produced anything approaching its surface regularity. We spend enormous effort polishing things to flatness, and a neutron star achieves something orders of magnitude beyond that through gravity alone. The most precisely shaped object in the universe was not made by craft or care, but by the relentless arithmetic of collapse. There are mountains on a neutron star, which is itself a sentence worth pausing on for a moment. The crust of this object is solid, and it is solid in a way that makes steel seem pliable, being many billions of times stronger than the toughest alloy we have ever produced or imagined. Despite that extraordinary rigidity, the surface cannot resist the gravity pressing down on it from all directions at once. The tallest peak a neutron star's crust can hold rises only a few millimeters above the surrounding terrain. A whole range of mountains, compressed by gravity into formations no taller than a coin set on its edge. If you were to stand somewhere and look toward the horizon, which itself would curve sharply upward rather than falling away, you would see a surface so flat, and even it would register as featureless. The most level ground in the known universe is not a salt flat or a still lake. It is the surface of a dead star, made perfectly level not by water or wind, but by the weight of its own existence pressing everything equally down. Many of these stars rotate, and some of them rotate at speeds that seem like they belong to a different physical world entirely. A young neutron star can complete tens of full rotations every single second, carrying its entire enormous mass around its axis each time with perfect regularity. The fastest known example turns approximately 700 times in a single second, its equatorial surface moving at a meaningful fraction of the speed of light. That number is not approximate or rounded for convenience. It is derived from the precise timing of the signals these stars send outward, signals that arrive at our instruments with a regularity rivaling the finest atomic clocks. Some neutron stars sweep narrow beams of radio waves through space as they turn, and when one of those beams happens to sweep across Earth, we receive a brief clean pulse once per rotation with extraordinary precision. The universe built clocks long before we thought of building them, and it built them out of collapsed stars turning quietly in the dark. Beneath the surface, the interior of a neutron star reaches into territory our physics can only approach with careful reasoning rather than direct observation. The neutrons below the crust may flow in a state that has no equivalent in everyday experience, a superfluid that moves without any friction or resistance, never slowing, never dissipating, simply continuing forever in whatever direction it was set. Closer to where the crust begins, the matter may take on shapes that physicists have given names borrowed from a kitchen, because the universe occasionally cooperates with humor. Sheets and tubes of nuclear material twisted into configurations found nowhere else in nature. Formation scientists have nicknamed nuclear pasta for reasons that are not hard to imagine. We will very likely never see these layers directly, not because we lack the inclination, but because no signal we can send would survive the journey in and back. What we know of the interior comes from careful inference, from the timing of the star's spin, from the way it occasionally shudders, and from the mathematics of matter under pressures that exist nowhere else we can reach. When a neutron star is first born, in the violence of the collapse that creates it, its surface temperature reaches roughly 1 million degrees. That heat glows not in any light our eyes can detect, but in wavelengths far above the visible range, a fierce radiance pouring off the newborn remnant into the surrounding dark. And then, with nothing more to sustain it, the star simply begins to cool. There is no hurry in this process. There is no deadline, no destination, no force urging the cooling to proceed at any particular pace. The star loses its heat across timescales that make a human civilization feel like an afternoon, slowly settling into the quiet of its surroundings the way a stone left outside gradually takes on the temperature of the air. It asks nothing of time. It simply persists, turning and cooling across spans that have no name in any calendar. This is where the first softening of the picture begins to arrive, because a star that exists on that kind of timescale is not urgently doing anything at all. There's a quality to these objects, once you sit with them long enough, that begins to resemble something closer to stillness than severity. Everything about a neutron star is extreme in the most technical sense of the word: the density, the gravity, the spin, the temperatures of its early life. And yet for all of that, it is also among the most balanced and self-contained objects the universe has built. It is smooth. Its rotation is steady. It holds itself together against its own gravity without trembling or failing, balanced at a threshold that allows it to exist without tipping over into something even more collapsed. The information it sends us travels in the form of a patient, rhythmic tick, arriving across light years with more consistency than most instruments we have built from scratch. You could set your understanding of time to it. Stars like this have been spinning in the dark since long before the sun first ignited, and most of them will still be spinning long after the sun has spent itself. They hold nothing against us. They threaten nothing we care about. They simply turn. The story of how we first recognized these objects for what they are is one of the quieter moments in the history of science, and it carries a certain gentle irony. When the first regular pulses were detected arriving from a fixed point in the sky, repeating with such precision that they seemed almost too orderly to be natural, the astronomers who found them were genuinely unsure what they were looking at. For a brief period, with more humor than certainty, the signal was noted as something that might conceivably have originated from an intelligence very far away. So perfectly timed did the pulses seem that the ordinary explanations felt, momentarily, insufficient. The true answer turned out to be stranger than that and more beautiful. A collapsed stellar remnant, sweeping its beam across space with the faithfulness of a lighthouse on a rotating tower, keeping time across the galaxy with no mechanism more complicated than spin and physics. What had seemed like a message was instead the simple announcement of a dead star, still turning, still counting the seconds in its own long arithmetic. The balance that allows a neutron star to exist at all is worth noticing before we leave this place, because it is genuinely fine. As the core of a dying star collapses, the neutrons themselves resist being compressed further, and that resistance is what stops the collapse and holds the star in its final form. But this support is not unlimited. If the remnant carries too much mass, somewhere above roughly 2 to 3 times the mass of our sun, even the resistance of packed neutrons cannot hold, and the collapse continues into something from which nothing, not even light, returns. A neutron star occupies the narrow zone between ordinary collapse and absolute disappearance, just heavy enough to have crushed normal matter entirely out of its original form, and just light enough to stop short of vanishing from the observable universe altogether. It is one of the most precisely balanced thresholds in all of nature, holding itself quietly at the edge of 2 different kinds of impossible. So we let the neutron star rest where it is, that level and impossibly dense remnant spinning in the dark, and we turn now to something stranger still, a close cousin whose extremity lives not in its weight, but in an invisible force that surrounds it. Among all the objects in the universe, the one we turn in now is defined not by what it is, but by what it carries. Where the neutron star was a study in compressed matter, this next place is something more invisible and more reaching. Its extremity does not live in its surface or its spin, but in a field that extends outward through empty space, reshaping everything within its range without touching anything at all. This is the magnetar, a close relative of the neutron star, and rarer than almost anything else the cosmos has managed to build. Only a few dozen have ever been found across the entire galaxy, which itself contains hundreds of billions of stars. Each one is young as these objects measure youth, thousands of years old rather than billions, a brief and fierce interval in the long calendar of the cosmos. The field it carries is not a detail of its nature, but the whole point of it. Everything extreme about a magnetar lives in that invisible surrounding force, a thing you cannot see or touch, but that rewrites the rules of matter simply by being present. The strength of that field is a number that refuses to sit quietly in the mind the way ordinary numbers do. Every magnet you have encountered in your life, including the ones that hold notes to a refrigerator door, operates in units that would be laughably small by comparison. The Earth itself is a magnet, gentle enough that a thin needle balanced on a pivot will swing toward its pole from anywhere on the surface. A magnetar's field runs roughly 1,000 trillion times stronger than that planetary field beneath your feet. Setting that figure against something familiar is not easy, because nothing familiar comes close to providing the right scale. The strongest magnets humans have built for use in medical imaging, already powerful enough to pull metal objects across a room, would register as negligible beside a magnetar. It is not simply a stronger version of something you already know. It is a different category of force, operating at an intensity that has no parallel anywhere in daily experience. At that level of strength, a magnetic field does not merely push and pull on iron or bend compass needles in an interesting direction. It begins to alter the fundamental geometry of atoms. The electrons that surround an atomic nucleus normally occupy roughly spherical clouds, and that rounded shape is part of what makes chemistry work the way it does. Within a few thousand kilometers of a magnetar, the field would stretch those clouds into thin, elongated rods, distorting every atom in any nearby substance into something unrecognizable. The chemistry that holds a body together, or a planet, or any piece of ordinary matter would quietly come undone. Not through heat, not through impact, not through any violent event, but through the silent and persistent pressure of a field pressing outward from a spinning remnant of a dead star. It is one of the few places in the universe where force alone, without drama or explosion, unmakes the structure of familiar things. The origin of such a field lies in the violence of the magnetar's own birth, which is worth understanding because it explains why these objects exist at all. When the core of a giant star collapses, the newborn remnant can in some cases spin with extraordinary speed in those first moments, rotating many hundreds of times per second while also churning internally. That rapid, early motion works like a dynamo of unimaginable scale, winding the magnetic field up to a strength that ordinary rotation alone could never explain. The result is locked into the structure of the star itself, a reservoir of energy stored not in heat or spin, but in the configuration of the field surrounding it. Once wound to that intensity, the field does not relax quickly. It holds its strength for thousands of years, pressing against the rigid crust of the star from within, straining the solid layers in the way that tectonic stress strains the ground before an earthquake. The crust of a magnetar is under constant siege from the very field that defines it. From time to time, that strain exceeds what the crust can hold, and the result is a sudden small adjustment, a kind of starquake in which the solid outer layer cracks and shifts into a new arrangement. When that happens, the magnetic field snaps with it, releasing stored energy in a burst of high-energy light that travels outward across the galaxy. A single large flare from a magnetar can, for a brief fraction of a second, shine more brightly in that kind of light than every other star in the Milky Way combined, all several hundred billion of them, outshined simultaneously by one cracking remnant no wider than a small city. This is not a gentle event by any local measure, and the scale of it is difficult to set against anything in ordinary life. The flares range from modest and repeated to genuinely enormous, and the largest ones represent a release of energy that the sun would need many thousands of years of steady burning to match. A single brief adjustment in the crust of a spinning remnant, and the output exceeds the sun's entire millennia of output. One such burst arrived at Earth some years ago, originating from a magnetar tens of thousands of light years away, a distance so vast that its light had been traveling since long before human history began. Even after crossing all of that empty space, bleeding energy into the dark with every light year of travel, the burst carried enough force when it arrived to gently disturb the uppermost edge of our atmosphere, that thin and fragile boundary where our air thins into the vacuum of space. It did not cause harm. It left no trace that anyone standing on the ground could have perceived. It simply registered in instruments designed to notice exactly the kind of faint and distant signal, a soft ripple arriving from something unimaginably far away. What is worth holding is not the force it once had at its source, but how completely that force spent itself across the distance, arriving here as a whisper that required sensitive machinery to hear it all. There's a thought experiment that physicists sometimes use to give a sense of the field's reach, and it is worth entertaining briefly before setting aside. If the nearest magnetar were somehow brought as close as the distance of the moon, which is itself a distance that takes light more than a second to cross, the field surrounding it would reach the Earth and affect the magnetic strips on every card and every wall on the planet, along with the workings of every electronic device, all at once, without any heat, without any sound, without any visible sign that anything was happening at all. Everything magnetic would simply stop working. The nearest magnetar is, in reality, not at the distance of the moon, but many thousands of light years away, a separation so enormous that the field has no practical reach anywhere near us. The thought experiment is not a warning. It is only an image, a way of feeling the scale of the force involved before releasing it back to its proper place in the far dark. These objects do not last in their intense form forever, which is one of the reasons so few of them have been found. The fierce field that defines a magnetar is not a permanent feature of its structure, but a temporary condition, one that gradually decays as the stored energy bleeds away through the repeated starquakes and flares over thousands of years. As the field weakens, it warms the star from within, and slowly the magnetar settles toward the quieter life of an ordinary neutron star, its great distinguishing force spent. The most intense magnets the universe builds are also among the most temporary things in the galaxy, burning brightly in the magnetic sense for a brief interval before fading into something far more ordinary. Each one is a brief visitor in the long history of its host galaxy, flaring for a cosmically short while before going still. There is something almost poignant in that arc, a thing so extreme it exists in a category of its own, spending itself across a few thousand years and then quietly disappearing into the background. The most reassuring feature of the magnetar, and in a way the most defining one, is how completely the distance neutralizes its power. A force that can rearrange the atoms of matter at close range becomes, across thousands of light years of empty space, nothing more than an occasional faint signal arriving at a patient detector. The field that would silently unmake chemistry at close range reaches us as something a sensitive instrument can barely distinguish from background noise. This is the consistent truth that emerges from every stop on this tour. The universe's most extreme places are also the universe's most remote ones, and remoteness does what no shield or barrier could accomplish. It turns the unreachable into the merely observable. The magnetar is the strongest magnet in creation, and also one of the most solitary objects in existence, spinning alone in a distant corner of the galaxy, its field slowly settling towards stillness with no audience and no consequence for anything near us. We do not need to fear it. We need only notice it the way you might notice a distant light on a far shore and then let it go. The magnetar turns in its isolation, its great invisible field pressing outward into empty space, touching nothing, threatening nothing, slowly winding down from something extraordinary towards something much quieter. It is in its own way a reminder that the universe's most powerful forces tend to exhaust themselves, that intensity does not sustain itself indefinitely, but eventually settles into calm. And from this place of invisible force and slow decay, we turn now to something that is not a remnant at all, but a living star still burning, one whose extremity lies not in what it has become, but in what it simply is, a scale so vast that the mind keeps sliding off the edges of it. And from that slow magnetic fading, we arrive now at something that has not yet ended, a star still burning. These are not the compact remnants we have been visiting, but living objects of almost incomprehensible scale. The red hypergiants are the largest single structures the universe assembles from ordinary stellar material, and their size is the kind that requires a new vocabulary to approach honestly. If you placed one of the largest among them where our sun now sits, its outer edge would reach past the orbit of Mars, and in the most extreme cases, would extend beyond Jupiter entirely. The inner planets would not orbit around such a star. They would be submerged within it, turning inside its glowing body the way a stir of sediment turns inside a glass of water. Our entire inner solar system, Mercury and Venus and Earth and Mars with all their accumulated history, would lie deep within the star's own volume, inside it rather than around it. The mind tries to hold this and keeps losing its grip, which is itself a useful thing to notice. Some scales are not meant to be fully grasped so much as briefly inhabited before being released. Light, which is not slow by any ordinary measure, would need several hours to travel from one side of such a star to the other. That single comparison does more than most numbers can. You already know how far light travels in 8 minutes, the distance from the sun to the Earth, a span so wide that nothing built by human hands has crossed it under power. Now extend that crossing time to hours, and you begin to feel the true width of what we are describing. Yet for all that volume, these stars are not dense in the way their size might suggest. The outer layers are spread so thin that near the surface, the gas is less substantial than what we would call a vacuum inside a laboratory here on Earth. A hypergiant is in its outer regions something closer to a vast luminous fog than a solid body, a near emptiness so enormous that it glows. There is no surface to approach in any meaningful sense, no boundary where a traveler might land or stand. Descending into such a star would mean entering a slow thickening of light and gas, growing denser and hotter with depth, without any single moment of arrival. The extremity of a hypergiant is not sharpness or solidity, but pure, almost abstract magnitude. These giants earn their place on this tour through what is happening inside them, which is nothing like what their slow exterior suggests. A massive star lives by fusing lighter elements into heavier ones in its core, and for most of its life, this process is steady and unhurried, hydrogen becoming helium across millions of years of quiet burning. But the later stages do not follow that pace at all. Once the hydrogen is spent, the star moves on to helium, and then to carbon, and then to neon and oxygen, each stage burning through its fuel faster than the one before. The architecture this creates is something like the layers of an onion, each shell fusing a heavier element than the one outside it, all the way down to the innermost layer where the final fuel is being consumed. The star is not exploding or visibly changing. From the outside, it looks much as it always has, a vast red lantern hanging in the dark, shedding light without apparent urgency. But inside, the pace of change is accelerating towards something it cannot avoid, like a river that flows gently for miles and then drops without warning into something entirely different. The final stages of that inner burning proceed at a pace that is almost difficult to believe. Where the initial hydrogen burning may sustain a star for many millions of years, the fusing of silicon into iron can be finished in roughly 1 to 2 days. A single day or two, and then the fuel for that stage is gone. The core temperature during these last stages climbs past 1 billion degrees, a figure so far beyond the heat of any surface that it occupies a different category of experience entirely. The star races through its remaining fuel with a kind of unstoppable momentum. Not because it wants to, but because each successive stage requires higher temperatures to sustain, and higher temperatures burn faster, and faster burning races to the next stage, and so the sequence compresses toward its conclusion like a piece of music that keeps accelerating. The star does not know it is approaching an ending. It is simply following physics, each step a consequence of the last, the whole progression as inevitable as arithmetic. The outside observer would see nothing unusual. A great red star dimming and brightening slowly, breathing in and out across long cycles. giving no outward sign of the swift collapse approaching at its center. The problem arrives when the burning reaches iron, and the problem is absolute. Every element the star has fused up to this point has released energy in the process, energy that pushed outward against gravity and kept the star from collapsing under its own weight. Iron does not release energy by fusing further. It absorbs energy. When the core becomes iron, the fire that sustained the star against gravity simply goes out. There is no gradual dimming, no slowing fade. The support vanishes, and gravity, which the star has held at bay across its entire life, wins. What follows is the collapse of the core, which happens in less than 1 second. The inner region of a star many times larger than the sun, falling inward faster than any ordinary event can prepare you for. The whole of that collapse, millions of years of stellar life undone in under a second, produces what we call a supernova. Before we follow the collapse itself, it is worth one more moment with a living star, resting in those final ages before the end, vast and red and dimly glowing against the dark with no outward sign of what waits inside it. The collapse is among the most violent individual events in the known universe. And yet even here the distance turns it peaceful before it reaches us. The core falls inward at a fraction of the speed of light, reaching densities comparable to a neutron star in under a second, and then abruptly resists further compression and rebounds. That rebound sends a shock wave outward through the infalling outer layers, and the result is the ejection of the star's entire outer body into space at speeds between 10,000 and 30,000 kilometers per second. The energy released in those first seconds exceeds everything the sun will produce across its entire 10 billion year life. Nearly all of that energy is not carried by light, but by neutrinos, particles so reluctant to interact with matter that they pass through the collapsing star as though it were not there, streaming outward in their billions of trillions and carrying the supernova's true power invisibly into space. The visible light arrives later, as the shock reaches the surface and the outer layers ignite, brightening over days into something that can outshine an entire galaxy of hundreds of billions of stars. That blazing peak then fades across weeks and months, its glow sustained by the slow decay of freshly forged elements. The star's last light, a record of its ending written in the chemistry of scattered debris. The most personal thing this tour will offer is contained in what happens during the blast. The temperatures inside the shock reach billions of degrees, and in that furnace the conditions allow something that no ordinary star can manage. Elements heavier than iron, which cannot form through steady stellar fusion, are forged in the intense and sudden pressure of the explosion. The calcium, now held quietly in your bones, was made inside a star and scattered by an event like this one. The iron that your blood uses to carry oxygen to your fingertips right now was forged in a stellar core and flung into space by a supernova that predates the sun. The oxygen you are breathing as you rest, drawn in and out with no effort while you lie in the quiet of this night, was assembled inside a star long before the Earth existed and released into the galaxy to drift until gravity gathered into a world. You're made of this material, not metaphorically, but literally, in the most precise chemical sense that the word literally allows. The atoms in your body pass through at least one stellar death before they were yours. And that passage is not a dark fact, but a quietly astonishing one. You're not watching the origin of the elements from a distance. You are the elements, resting now in a temporary and extraordinary arrangement. A supernova must occur within roughly 25 to 50 light years of Earth to cause serious damage to our world, and there is no star within that range both massive enough and old enough to pose any such risk. The giants capable of this kind of ending are far away, embedded in distances that make their power academic rather than relevant to any evening. What we receive from even the nearest supernovae is a gradually brightening point of light that fades over weeks, followed by an expanding cloud of glowing debris that spreads outward for thousands of years. Long before anyone understood what they were, people on Earth occasionally noticed a new star appear in a sky they knew well, bright enough in some cases to be seen in full daylight, lingering for weeks or months before fading back into dark. They were watching the death of a star that had ended its life across an ocean of light years, its last light finally arriving after a journey of thousands of years. Those observers had no name for what they were seeing, no framework for the collapse and the shock and the scattered elements. They simply noted the new light and watched it fade, unaware that they were witnessing an act of cosmic creation as much as an ending. What a supernova leaves at its center is either a neutron star, the kind we visited first tonight, or for the most massive progenitors, a black hole. Around that central remnant spreads an expanding shell of glowing gas, the scattered outer layers of the original star still moving outward years and centuries and millennia after the explosion. These remnants are among the most graceful things the sky contains. Slow-blooming structures of color and light that mark the place where a star once ended and a new scattering of elements began. The material drifting outward from a supernova will eventually disperse into the surrounding space, thinning across light years, mixing with the gas between the stars, and over vast stretches of time, gathering again under gravity into new clouds, new stars, new planets. On at least one small world near a modest star in an unremarkable arm of an ordinary galaxy, the gathered material produced living things that can look outward at the night and wonder where they came from. The answer is there in the dark, held in every distant point of light that has ever ended, and the quiet atoms that carry the memory of those fires into whatever comes next. We are, in the most literal sense, made from the calm ash of those distant fires, and we carry that with us as we move on. A supernova is not only an ending. It is the means by which the material of one generation of stars becomes the material of the next, the most violent events in nature turning out to be, across the long view, the gentlest acts of inheritance the cosmos knows. The first fire spent itself. The elements drifted. Gravity gathered them again. Something small and warm and aware was the result. Lying somewhere on a quiet world in the arm of a galaxy, breathing air forged in a star, resting on iron laid down in a stellar collapse, held together by calcium that once passed through one of the most extreme events in the universe and came out the other side as something ordinary and essential. The tour does not end with the supernova. It continues from it, following the scattered elements to places where extremity takes a different form, where not one dead star, but two find each other in the dark, and where their meeting makes something that fits in the closed hand of a person who will never know where it came from. Sometimes two dead stars find each other, and what follows is the slowest courtship the universe knows how to stage. They were born together, two massive suns sharing a common origin in the same ancient cloud of gas. Each one lived its separate life, burning through its fuel across millions of years of quiet stellar time. Each one ended as a dense and spinning remnant, collapsed to a sphere no wider than a city, carrying the mass of a sun in that impossible compression. And then, because gravity is patient beyond any ordinary meaning of the word, those two remnants began the long work of drawing closer. The approach takes millions of years, sometimes longer, the orbit tightening by amounts too small to register across any human span of watching. With every turn around their shared center, they shed the faintest trace of energy into space as ripples in the fabric of space-time itself. Those ripples carry away the orbit's momentum so gradually that no clock we could build would register the change from one year to the next. The whole of recorded human civilization would pass inside such a system without producing any visible change in the gap between them. And yet the arithmetic is relentless, and the gap does close, one imperceptible fraction at a time. The final stage arrives without ceremony after all that patience, compressing millions of years of slow approach into a handful of frantic seconds. As the two remnants close the last distance between them, their orbit tightens so rapidly that they begin circling each other hundreds of times per second, whirling around their shared point in a blur of motion that strains what physics allows for objects of such mass. In those last moments, the system is generating gravitational waves of growing intensity, ripples in space-time spreading outward in every direction at the speed of light. The waves carry the story of the merger across the entire observable universe, thinning with distance the way all signals thin, arriving at the far edges of the cosmos as something almost too faint to name. When such a wave reaches us after traveling hundreds of millions of light years, it stretches and squeezes the space around us by an amount smaller than the width of a single proton. That is not a rough estimate or a figure chosen for drama, but the actual, measured scale of what our instruments have learned to feel. We built machines of extraordinary delicacy specifically to register that impossibly small tremor, and we succeeded, and through that success we gained a new way of listening to the universe. The merger of two dead stars shook the shape of space, and we felt it, gently, like a single note played in a very large and otherwise silent room. The collision itself lasts an instant, but what it produces will drift through the galaxy for longer than our species has existed. When the two neutron stars finally touch and merge, the conditions at the point of contact exceed anything found at the center of any living star, temperatures and pressures for which are physics as equations, but no physical intuition. In that brief and extraordinary furnace, something happens that ordinary stellar fusion cannot accomplish. The lightest elements fuse upward through heavier and heavier forms in a rapid cascade, building atoms that no star's slow interior could ever assemble. Gold is made here, and platinum, and a catalog of rare heavy metals that exist nowhere else in any abundance the universe produces. A single merger of this kind can forge many times the mass of the entire Earth in precious metal alone, scattered outward into the surrounding space in the minutes and days that follow. The gold in a ring, the platinum in a catalytic converter, the iridium in certain instrument components, all of it traces back to moments like this one, collisions between dead stars that happened before the sun was born. The most extreme collision the universe can stage is also the origin of the quietest and most familiar treasures in your immediate world. After the merger, a glow spreads outward from the site, fed by the decay of all the freshly made elements settling into their new forms. This afterglow, called a kilonova, shines across many different kinds of light simultaneously for days before fading, a bloom of radiation marking the place where two remnants finally met. It is one of the rare events in astronomy that we can detect in more than a single way, feeling its gravitational tremor in the shape of space, while also seeing its light with ordinary telescopes pointed at the same patch of sky. Two entirely different senses confirming the same distant happening across the same moment of cosmic time is a genuinely new thing in human experience, something that became possible only recently, and that continues to feel like a gift each time it happens. Then the kilonova fades, and the sky returns to its long quiet, and the new elements begin their slow drift through time. The gold scattered by that merger will travel the galaxy for billions of years, mixing into clouds, settling into new stars, falling eventually onto new worlds where something might one day reach down and pick it up, not knowing where it came from or how old it truly is. From a meeting of two dead stars, the tour moves now to the most luminous events the universe produces, moments so bright they briefly outshine everything else in the observable cosmos. Gamma-ray bursts are not steady places, but events, narrow beams of energy fired across the dark and then gone, each one lasting from a fraction of a second to a couple of minutes at most. They come from two different kinds of violent endings. The longer ones are born when a massive and rapidly spinning star collapses directly into a black hole without leaving a neutron star behind. The shorter ones come from the kind of merger we just visited, the meeting of two dense remnants generating a black hole and a burst in the same cataclysmic instant. In either case, the black hole that forms at the center becomes surrounded by a swirling disk of infalling matter, and from the poles of that disk, two jets of material are fired outward at more than 99.9% of the speed of light. The energy focused into those jets is almost unreasonable in its scale, a single long burst releasing more total energy than the sun will produce across its entire 10 billion year existence. That figure is not selected for effect, but derived directly from measurements we have made of actual events detected from billions of light years away. The narrowness of those jets is the reason these events, for all their staggering output, present no concern for anything alive on any quiet world. A gamma-ray burst is not a sphere of energy expanding in all directions like an ordinary explosion, but a tightly focused beam, a lighthouse whose cone of light covers only a thin slice of the surrounding sky. The rest of the universe receives nothing from it at all. For such a beam to matter to Earth, It would need to be aimed almost precisely along the line connecting its source to our planet, from a star close enough for the beam to retain meaningful intensity across that distance. A coincidence of geometry and proximity so unlikely that across the long history of our world, it has effectively not occurred. There are no stars within the necessary range that are both suitable and aimed correctly, and the vast majority of bursts we detect originate from galaxies billions of light years away, their energy long since thinned by the enormous journey. What we receive from even the most powerful of these events is a brief brightening in our instruments, a faint point of light that rises and fades across minutes or hours, followed by a slowly dimming afterglow that lingers for days before dissolving into the background dark. There is a quiet comfort in the delay built into everything we observe from these extreme distances. The light we catch from a gamma-ray burst that originated billions of light years away left its source when the universe was a fraction of its current age, when the stars that made it had not yet given way to the calmer galaxies that surround us now. We are not watching something happening in the present moment, but reading a very old letter that required an almost incomprehensible journey to arrive. The burst flared, the jets fired, the afterglow bloomed and faded, all of it billions of years ago in a galaxy whose shape has entirely changed since then. What reaches us now is only the light, thinned and ancient, telling us only that the universe once did something extraordinary in a place and time that has no remaining connection to anything we could reach or touch. There is a kind of comfort folded into that delay, a knowledge that the most violent events in nature arrive here, softened by time and distance into something the instruments can barely measure and the eye cannot see unaided. The two types of gamma-ray bursts offer a picture of how the universe connects its most extreme events in unexpected ways. The long bursts trace back to the deaths of certain massive stars, the very kind of giants whose lives we followed in the previous section, now ending not as supernovae that scatter their elements gently, but as collapses fierce enough to fire jets clear across a surrounding galaxy. The short bursts trace back to neutron star mergers, the same collisions that forge gold and shake the shape of space with gravitational waves, producing a burst as a byproduct of the same catastrophic meeting. Two very different events at opposite ends of the stellar story. One the death of a single living star, and one the delayed reunion of two long-dead remnants, both capable of producing the same blinding blade of energy aimed at nothing in particular. The universe does not seem to reserve its most extreme outputs for any single mechanism, but finds multiple routes to the same extraordinary destination. And in both cases the result, for anyone not directly in the path of the beam, is a brief and harmless brightening in a patch of distant sky, carrying news that something remarkable happened a very long time ago, far away, in the deep history of a cosmos that was already old before the Earth existed. We turn now from the brightest events to the largest sustained light sources the universe has ever built, the blazing centers of certain ancient galaxies that outshone everything around them by factors that resist ordinary description. These are the quasars, the engines of the early universe, and their power comes not from any explosion, but from the continuous fall of matter toward a black hole so massive that its appetite generates more light than the combined output of every star in a typical galaxy. A quasar forms when a supermassive black hole, the kind that anchors the center of a large galaxy, is surrounded by a generous supply of gas that has not yet been gathered into stars. That gas does not fall straight inward but spirals, forming a disk of circling material that heats through friction to temperatures of hundreds of thousands of degrees near its inner edge, blazing across many kinds of light simultaneously. The disk itself is the light's source, not the black hole, which remains as dark as ever, its event horizon invisible at the center of all that radiance. A bright quasar pouring out the equivalent light of 1 trillion suns does so from a region not much larger than our solar system, a space we would consider small, producing a brightness that overwhelms an entire surrounding galaxy of hundreds of billions of individual stars. These brilliant engines belong mostly to the early universe because they required a fuel that the young cosmos had in abundance and that later ages gradually used up. In those first billion years, vast quantities of loose gas were available to fall toward the giant black holes forming at galactic centers, and the result was an era of extraordinary brightness, the most luminous sustained period the cosmos has ever produced. As the ages passed, that gas was consumed or gathered into stars, the disks thinned, and most quasars quieted into something much calmer, their host galaxies settling into the relatively peaceful state we see in the universe around us today. Many galaxies that once held blazing quasars now hold only dark and silent centers. The engines banked low, the fuel spent, the era of great fires largely behind us. The light we receive from the brightest quasars left its source when the universe was young and the Earth did not exist, traveling for billions of years to arrive at our instruments as a faint point indistinguishable to the naked eye from an ordinary dim star. That a trillion suns of brightness should arrive here looking so modest is one of the quieter demonstrations of what distance does to even the most extreme output. The most luminous, steady objects the universe has ever made reach us as gentle points in the dark, ancient lanterns burning at the edge of sight, their fury long since softened into something we could lie beneath and never know. And from those ancient engines cooling at the edge of sight, we arrive now at the place where everything began. This is not a location you can point toward in the sky or mark on any map of the cosmos. It is instead a moment, the earliest moment, the one from which all other moments grew. Everything that has appeared on this tour tonight, the neutron stars and magnetars, the supernovae and their scattered ash, the merging remnants that forged gold, the blazing quasars, the wandering dark objects crossing empty space, all of it traces back to a single origin so extreme that the word extreme itself feels inadequate beside it. In the earliest instant we can reasonably describe, everything that now fills the observable universe was gathered into a space smaller than a single atom. Not compressed into that space the way water is compressed into a container, but genuinely occupying it, all of matter and energy and the fabric of space itself folded into something that makes a neutron star seem spacious by comparison. The temperature exceeded anything that has existed since, hotter than the center of any star, hotter than the cores of any supernova, hotter than any condition the universe has managed to recreate in the long ages that followed. It was not an explosion inside an existing empty room. It was the swift expansion of space itself, carrying everything along as it grew outward in every direction simultaneously. In the very first fraction of a second, before any structure had formed or could form, the universe passed through a stage of sudden and enormous stretching. This brief inflation expanded the young cosmos by a tremendous factor almost instantaneously, smoothing out irregularities that might otherwise have left the universe lumpy and uneven at large scales. What it also did, and this is the part that connects the beginning to everything that came after, was preserve certain faint ripples in the distribution of matter, tiny variations in density laid down during that first swift expansion. Those ripples were not errors or accidents, but the seeds of everything that would eventually grow under gravity into galaxies and clusters in the vast cosmic web. Every bright structure we have visited tonight, every galaxy hosting a quasar, every nebula seeding new stars from supernova ash, every system where two neutron stars found each other after billions of years, all of it grew from the pattern set in those first moments of stretching. The beginning did not merely produce matter. It wrote the instructions for everything the universe would eventually become. For the first tiny fractions of a second after that inflation, the universe was too hot for the building blocks of atoms to hold together in any familiar arrangement. The particles that now constitute protons and neutrons flowed freely in a kind of formless sea, bound to nothing, moving in conditions that no laboratory on Earth has approached and none likely ever will. This plasma of the most fundamental particles carried no chemistry, no structure, no distinction between one region and another. The whole cosmos was a single undifferentiated furnace with no inside and no outside, no here and no there, only heat and density beyond all analogy. Then, as expansion continued and the temperature dropped, those fundamental particles began to combine. Within the first 3 minutes, a span of time so brief it would pass unnoticed in most contexts, protons and neutrons joined into the first atomic nuclei. The recipe assembled in those minutes still describes the ordinary matter of the universe today, mostly hydrogen, a substantial measure of helium, and only the faintest trace of anything heavier. Everything more complex, every carbon atom in every living thing, every iron atom in every star, had to wait for the stars themselves to build it across the long ages that followed. For several 100,000 years after that first fierce light, the universe remained too crowded for photons to travel freely. The young cosmos glowed throughout its entire volume, but was opaque, a fog of charged particles through which no clear beam could pass or carry information across any distance. Then, as the temperature fell further and electrons settled on a nuclei to form the first complete atoms, the fog cleared. In that clearing, light that had been trapped and scattered for hundreds of thousands of years was suddenly set free, streaming outward in all directions through a now transparent universe. That ancient light is still traveling. It has been traveling ever since, stretched and cooled by the long expansion of space. Its original fierce glow thinned across billions of years into the faint background warmth that fills the sky in every direction today. The cosmic microwave background, as it is known, is the oldest light there is, the cooled remnant of the first fire still gently present all around us, arriving from every direction simultaneously, the universe's own record of the moment it first became clear enough to be seen. What makes all of this more than a beautiful story is that the universe left evidence, and the evidence can be checked. The proportions of hydrogen and helium and the trace heavier elements produced in those first minutes match closely what measurements across the cosmos actually find. The faint ripples in the background light carry within them the precise pattern of the density variations laid down during inflation, the same pattern from which all later structure grew. We did not witness the beginning, and we never could, but the universe kept a faithful record of it, written into the abundance of ordinary matter and the soft temperature variations of the oldest light in the sky. That such an extreme origin should leave behind so calm and so readable a record is its own kind of reassurance. The wildest beginning the universe is capable of settled into an order that patient instruments can study and that careful reasoning can trace backward through time. The most violent moment in all of existence produced, as its lasting inheritance, a cosmos legible enough for creatures made of its own cooled ash to eventually red. And now, before the tour closes, there is one more place to visit, and it is not a place in any ordinary sense of the word. It is a question, an open and honest one, sitting at the very edge of what human understanding currently reaches. Our finest physics tells us that empty space is not truly empty, but has properties of its own, an underlying energy, a state in which it rests. What remains unresolved is whether that state is the lowest and most stable one possible, or whether space might be resting in a condition that is merely stable for now, the way a ball resting in a shallow valley is temporarily settled, while a deeper valley lies somewhere below it. If the second possibility were true, then in principle space could someday shift to its true lowest state. This is called vacuum decay or false vacuum, and it lives at the meeting point of quantum mechanics and general relativity, exactly the place where our two great theories of nature are still incomplete and still, despite enormous effort, not fully joined. The question is not answered. It may not be answerable with the tools we currently have. It might sound like the kind of idea that should disturb a quiet evening, but consider its actual nature carefully, because the details take all the weight out of it. If such a transition could occur at all, it would propagate outward at the speed of light. That single fact removes any possibility of warning, preparation, or anticipation. A change that travels at the fastest speed anything in the universe can travel would arrive without a preceding signal of any kind. There would be no slow approach, no gathering sign, no darkening of any sky that an observer could notice and name. A thing that cannot be seen coming is by its very nature nothing that can trouble a single hour of any life. The vigil cannot be kept because there is no signal to wait for. This is not the reassurance of someone looking away from a real danger, but the straightforward consequence of the physics involved. The only rational response to a possibility that is by definition undetectable in advance is to set it gently down and return to the present moment, which is precisely where it belongs. And there is far more reason for calm than the mere impossibility of warning. As best we can measure, the state of empty space has held perfectly steady for nearly 14 billion years. Through the formation of every galaxy we have ever observed, through the birth and death of every star that has ever burned, through the assembling of every world that orbits any of those stars, including this one, space has remained exactly as it is. Whatever its deepest nature, it has demonstrated across the entire history of the cosmos a stability so consistent that the word reliable barely captures it. Everything we know suggests it will continue holding, unchanged, across spans of future time so enormous that they bear no relationship to anything a living creature could experience or anticipate. The universe has rested in this calm for longer than our minds can genuinely hold. And it goes on resting, steady and unchanged, while we in our brief moments sit inside it and breathe. The deepest uncertainty at the far edge of physics turns out to rest upon the deepest reliability there is. What this final question really leaves us with is not unease, but a particular kind of humility, and it is the gentle kind. It tells us that even now, after everything we have learned, the universe still holds a few of its doors quietly closed. There are still edges to the map, still places where the known fades softly into the unknown, and we have lived our entire history alongside such edges without being diminished by them. Not every mystery is a warning. Some are simply the universe admitting honestly that not everything has yet been decided, and that honesty is its own kind of gift. The long stability of space is not a small thing to note in passing. It is the precise condition that made everything else on this tour possible, the steady ground on which galaxies formed and stars ignited and worlds gathered, and something small and warm and aware eventually opened its eyes within it. The calm of the universe is not an accident we happen to be enjoying. It is the same calm that allowed us to exist at all. So we let this last question rest where it belongs, at the quiet far edge of what we know, unsolved and untroubling, a door left softly ajar in the dark. The tour is over now, and it has carried us to the densest ground and the strongest field and the brightest engines and the coldest corners and the farthest edges of understanding itself. At every stop the same truth waited, patient and unchanged. The most extreme places in the universe are also the most distant, turning indifferently in their own darkness, asking nothing of us, threatening nothing we love, and having helped, in their way, to make the gentle world where you are resting now. The neutron stars are still spinning. The black holes are still turning. The first fire became, across 14 billion years of patient cooling, the soft dark of this ordinary night. Let the distance hold them all. Let your breathing slow. Let the night settle over you like the quiet between the stars. If these journeys are worth your time, a like or subscription helps others find their way here too. Sleep well and good night.